Okay, so in this tutorial we're going to talk about light as an electromagnetic wave, and then the more general electromagnetic spectrum. We're going to look at this chart that is right in front of us, and I'm going to point out some of the key things that we want to know about it, things that you have to memorize or you refer to understand. And then we're going to go into applications of each part of the electromagnetic spectrum. I'm going to elaborate on this, or may have already elaborated on this with some PowerPoint presentation, but we might as well write down what we are expected to know to make this a little bit more full to us, and we can appreciate the importance of the electromagnetic spectrum. We're just scratching the surface for much of this, but it's an important start to helping us understand the nature of light and ultimately modern physics. All right, so let's start with the basic question that we've already addressed in class. What is an electromagnetic wave? So we see a picture right below this statement where we have some sort of device that is creating charges to oscillate back and forth. And so we get a changing electric field with time. And because there's a changing electric field, there is a corresponding change in magnetic field that's at right angles to it. And they propagate forward in this z direction. And they propagate forward with the velocity v. So an electromagnetic wave is oscillating electric and magnetic fields at right angles to each other. Okay, so that's the first thing you would have to be able to define. And what do? Well, they transfers energy. Let's not forget that. That's often lost in the conversation about what exactly light is. It's a transfer in energy. It's electric and magnetic energy, and it travels at the speed of light at right angles to both the E and the B field. So note that the velocity vector is not in the same direction as the E field changes or the B field changes. Okay, I want to finish up on this. I don't have that. Because, let's add a third line here, because charges, right, that's very, very important. It could be electrons, protons, ions, anything, are, in most general sense, accelerating. Okay, there's lots of ways you can make charges accelerate. What we're describing off to the left is oscillating them back and forth. You could have charges moving at a constant speed and stop them suddenly, and you would get electromagnetic radiation. In fact, that's how X-rays are often produced. You could have charges going around in a circle at very high speeds. They'll give off what's called synchrotron radiation, which can be in the ultraviolet or X-ray part of the spectrum. You can have electrons being excited in atoms, okay, and then de-exciting, and in that process, they're going to give off light. You can have a nucleus be excited, or you could jiggle a nucleus and you will give off radiation. That's generally in the gamma part of the spectrum. So depending on the mechanism that you produce the electromagnetic radiation, you're going to get different types of radiation. And that's the radio, microwave, infrared, visible, ultraviolet, X-rays, gamma. So this is where the whole idea of the electromagnetic spectrum comes from. Okay, so let's talk about let's talk about what they all have in common, from radio to gamma. First of all, they all travel at the same speed. And of course, that's the speed of light given the symbol c, 3 times 10 to the 8th meters per second. I mentioned in one of the classes that this is now accepted as an exact value. It's not 3.0, but like 2.99 and a bunch of decimals. So the speed of light is so important and so fundamental in so many areas of physics that we've elevated it to an exact number. And we can build other quantities from that. I'm not going to go into great detail on that right now. The only difference then in the different parts of the EM spectrum are their wavelengths, okay, or frequencies. And we know that wavelength and frequency goes hand in hand, at least inversely. So the key equation we mentioned in class is the speed of the wave, c, equals lambda f. So if I choose a certain part of the spectrum, let's say I choose infrared right here, and I see infrared rays are roughly 10 to the negative 5th meters. Okay, they can go towards 10 to the negative 4th on this side, or they can veer towards 10 to the negative 6th. And I look at the corresponding frequency down here, I see that it's around just before 10 to the 12th. So let's say it's around 10 to the 11th. All right, if I, actually, that's way off, sorry. Okay, I don't know why I curved over. So if I go over, it's around here. So this is in a high 10 to the 5ths, 10 to the 12ths. So if I multiply 10 to the negative 5th times 10 to the 12th, I see that that's 10 to the 7th. And then since there's a coefficient in front of this one and in this one, that would bring it up to 10 to the 8th. The point being that if you take the frequency and the wavelength, the corresponding wavelength for any part of the EM spectrum, you'll get the same number, the speed of light. So you are expected to know that radio are long wavelengths on the order of meters, tens of meters, even higher, and that gamma rays and X-rays are extremely short wavelengths or high frequencies. You need to know within the visible spectrum, even though it's not on here, you need to know that in that order it's Roy G. Biv. Okay, so I put in that order because we're going from long wavelength to short wavelength, or we're increasing in frequency. You don't have to know specific values, but you should know that visible light, because of all the experiments we've done, are on the order of 10 to the negative 7th meters, or a few hundred nanometers, and which is on the order of 10 to the 14th hertz. Okay, so those are some things you want to be able to do from an estimation standpoint, and then realize infrared is longer wavelength or lower frequency, and ultraviolet is shorter wavelength or higher frequency. Another aspect of this that you would want to know is the relative size of them, how they compare to objects. And the reason this is important is for diffraction purposes. All right? So the fact that radio waves are on the order of size of buildings and humans is important, because if we're transmitting radio waves through the air for telecommunications, well, when they encounter a building or a person or something between, they're long enough in wavelength that they will diffract around them, so they're not easily blocked. Whereas if I want to look at, certain things with great detail right here, then I want things that are smaller than that, and that would be visible. So visible light is smaller than everything, so I can see a lot of great detail, because visible light's not going to diffract around it very easily. If I want to see atoms in that, visible light is useless because it's much bigger than an atom or a molecule. In fact, we get to the protozoa, then we can just we're getting to the limits of resolution, because the wavelengths are on the order of size of the object we're looking at. Something we'll talk about later on is how the type of electromagnetic spectrum corresponds to the temperature of the body, of the object in question. All objects, this is something we'll talk about in much greater detail when we do radiation physics in the spring. All objects emit radiation, which is EM radiation, because of temperature. So a classic example is the sun. The sun's temperature is around, at least at the surface of the sun, 6,000 degrees Kelvin. And because its temperature is around 6,000 degrees Kelvin, if I look at the intensity output of the sun in various wavelengths, I will see that it follows a spectrum like that. And most of the light is in this part, which is visible. Okay? In fact, the peak corresponds to green and yellow, and that's why our eyes are most sensitive to those colors. That's why the sun appears yellow, and that's why our eyes see in this part of the spectrum and not any other part of the spectrum, because that's what the sun puts out most. So that's really, really important. Whereas if we look at the Earth, on the other hand, the Earth is fairly cool, roughly 300 Kelvin, and because it's so cool, its spectral curve would look something like that, and this peaks around the infrared. So the Earth and all planets glow in the infrared, whereas hotter objects would go invisible. Hotter yet would start giving off more ultraviolet, and so on and so forth. So that's a very, very important relationship between temperature and the peak radiation. But that's getting ahead of ourselves a little bit. All right, another aspect we want to understand is transparency of our Earth's atmosphere. Not all those forms of radiation can penetrate the atmosphere. If you look closely here, you'll see only two types penetrate: visible light and radio waves. Most of the others are completely blocked or partially blocked. So our atmosphere is transparent, only a few forms: visible, okay, and that's what the output of the sun is, coincidentally, and radio. Other forms of radiation that we don't want to get in, UV, which is not good for us, is blocked by the ozone layer. And infrared radiation is trapped by greenhouse gases, which I'll call GHGs. We'll talk more about those another time, but your classic greenhouse gas is carbon dioxide. Okay, so we want to understand how different forms of radiation interact with our atmosphere, because it's so vital to what goes on at the surface of the Earth. We'll we'll have more to say about that later. All right, the last little thing we want to be aware of is the general source of how we get each one. I alluded to that earlier when I was talking about how we create radiation in the first place by accelerating charges. So let me just give you a more broad way of looking at that. Okay, so I'm going to break this up into 4 general zones. They're not perfect, but they do a pretty decent job of giving us an idea. So if I want to create radio and microwaves, generally what you do is you simply oscillate electrons in circuits. Okay, so it's more of a macroscopic property. You have electrons in a circuit or a transmitter, and they vibrate back and forth over some distance, and an antenna works by a similar fashion. If you want to start producing the higher frequencies, okay, you're not going to be able to generate those type of, giga or actually terahertz types of frequencies that would correspond to infrared or visible. It's just not going to be done electrically. So what you do is, in a general sense, you vibrate certain objects. So for this one, it's generally caused by vibrating molecules, really small things. Okay, and the charge is in there. If you want to start producing visible light and ultraviolet and even what we call soft X-rays, more towards the low end of the frequency of the X-rays, we would vibrate atoms, even smaller things. Okay, so that's getting into the excitation of electrons within atoms. You can think of that as a vibration of sorts. It's not a perfect analogy, but it gets the idea across. And if you want to start producing gamma radiation and X-rays at the hard end of things, then you want to vibrate something even smaller, and that, of course, is the nucleus. Okay, so when you mess with the nucleus in terms of causing excitations, etc., you will get gamma radiation. Okay, I'm going to stop here for now. What I'll do as a separate video tutorial how we can use each of the EM spectrum. Okay, so we will elaborate on some of this, especially the various forms and how they can be applied or how they're useful in astronomy in class.